There's a funny saying about minced meat. It's impossible to turn back time. And unfortunately, this saying often applies to everything that happens to us in life. There is only one interesting technique. You just need to create a time machine and make this time machine work as intended. But today, we'll talk about a more practical application of this rule and figure out what happens if you take a metal alloy and try to turn that metal alloy into the original components from which that metal alloy was obtained. So friends, in order to answer the question at hand, we need to have a clear understanding of what a metal alloy is. Let's take steel, often called black steel or cast iron. There was also an interesting video about cast iron, so be sure to check that out. So what is steel? It's an alloy of iron with carbon. So in the end, what do we get? Alloy. An alloy is a specific system created by melting together at least two components. But it could also be more than just two. With the formation of a specific structure and a certain configuration, steel is a new material from two old ones. We're interested in one thing that was formed as a result of the interaction of two old materials. And basically, we're primarily interested in just one thing. If we take an alloy of iron with carbon, that very steel or that very cast iron, let's imagine now that there are just two components, and this is a simple, of course, tool steel, where you have something like this, a wheel, or a dog like this, or a giraffe in the name, in the labeling. And we only have two components. So what we're primarily interested in is whether we can get back pure iron and pure carbon. Can we isolate them? Well, for that, let's continue our exploration, our discussion. What happens when we melt together two metal components? It's reasonable to assume that they engage in some kind of interaction, some interaction at the atomic level, and basically when all of this happened, when we got a common melt, when this melt became homogeneous, what can we say about this melt? We can say that in this melt, atoms of certain types are present in specific states. Now, in order to get a finished product from such an alloy, what do we need to do? We need to crystallize it. When a metal alloy crystallizes, the atoms in this metal alloy have combined so that it has become complex. Relating to different elements have combined in such a way, so basically it has become complex. A solid system, a solid crystallized system, and this crystallized system has certain characteristics. The characteristics include, among other things, the features of the internal ordering of these elements. And let's start with the simplest option for the interaction of atoms within a single obtained alloy. The simplest and probably the most well-known method, which you may have already heard of, is solid solutions. Solid solutions. This is not some kind of joke among material scientists, not some kind of joke among engineers. This is indeed the so-called state of alloys that results after crystallization. It resembles a liquid solution, and that's basically why it was named that way. There are several types of solid solutions, interstitial solid solutions and substitutional solid solutions. An interstitial solid solution is quite easy to visualize, and substitution is too, but let's start with interstitial. An interstitial solid solution forms when, during the crystallization of two elements together, one element builds its lattice, and the atoms of the other element are trying to squeeze into the lattice. It turns out, generally speaking, that there is implementation, and in fact, thanks to this, strengthening occurs. But strengthening is a separate topic, so we won't touch on it right now. In the case of an interstitial solution, the second impurity gets inserted into the main iron lattice, while in substitution this impurity replaces a vacancy. When the atoms of the other element try to squeeze into this lattice, they don't fit into its free spaces. Instead, they replace the atoms at lattice nodes. When the atoms of the other element enter this lattice, they don't fit into its gaps. They replace the atoms at the nodes, forming a substitutional solution, into its free spaces, but they replace the atoms located at the nodes of that lattice. So we end up with a substitutional solid solution, not interstitial, and basically it's not very easy to break down such a thing either. The next option that can form is a chemical compound. What is a chemical compound? Well, you and I remember, for two elements to combine, they need to establish a chemical bond. It is not at all necessary that exactly two metals will be present in chemical compounds, and that in the example under consideration we will have a chemical compound in the alloy consisting of exactly two metals. There could also be options with non-metals, but that's a whole different story. And just imagine a chemical compound for a second and think about how to separate it. It's like ground beef turning back into a cow from patties. The next option that can be found in metallic alloys is the interstitial phase. The interstitial phase is something that resembles, roughly speaking, a solid solution. So we end up with a certain phase, which gets inserted into the structure of the resulting crystallizing alloy and forms a separate phase, which is very easy to separate. And based on this, heterogeneous structures are formed, meaning diverse structures that, in general, are also classified as a separate type of alloys. There are also things like electronic connections, but we won't talk about them, because basically the logic is pretty much the same as what we had with chemical compounds. And there's also something called the Laves phase, which forms in cases where the atomic diameters of the atoms being combined into a single alloy differ. But we won't talk about that either, because technically it has a negligible influence on the issue at hand, and figuring this out is complicated and time-consuming. We didn't just go through all this boring and tedious theory for nothing. We needed it so that we could understand whether it's possible to extract the original components from the alloy, or if that's completely impossible. And I think you understood that in each specific case we are dealing with a specific type of interaction between the atoms that make up the resulting crystallized alloy. To separate these atoms we need to show some serious ingenuity and a bit of muscle. When do we have interatomic interaction? I think you understand that you can't just get away with it. The only option that is greatly simplified for us is heterogeneous structures. Well, in the case of more complex situations, where we have chemical compounds, where we have solid solutions of insertion and substitution, where we have different phases of Laves and other types of interactions between elements in a single common structure, creating such an action will be practically impossible. But it's practically impossible. That doesn't mean it's impossible. Fortunately for you and me, unlike Primera, where minced meat cannot be turned back, and where we cannot get a new cow from a cutlet. Without machines, we can use clever and complex methods to perform necessary actions and obtain raw materials in their original form. However, from an energy standpoint, this is unprofitable. The first thought is to recall the chemical method of influence. The other thing is that from an energy standpoint, this is a completely unprofitable procedure. And the first thing that comes to mind is to recall the chemical method of influence. Indeed, how can we get something from something else? Well, chemists came up with this clever method that is still practiced today, which was practiced in my lab when I worked there. You take something in a certain amount, that something dissolves in something, that something can dissolve. I'm saying you see how convoluted it is, but I hope you understand the train of thought. And in general, when something dissolves, we get something in the solution. Atoms in a separated state, and by the way, not always in a separated state, but predominantly in a separated state, if the solvent was suitable. And these atoms can be extracted from there in various ways. Through various precipitations, different chemical reactions, various electrolysis processes, and other methods, dissolved atoms become pure elements, complex in energy, which are already in a separated state, can be transformed into the original pure elements using additional techniques. But these techniques will be very complex, they will be very problematic, and will require a lot of energy. But in the meantime, let's move on to the second method, and this second method is, as you understood to some extent, an auxiliary method is electrolysis. As you remember, aluminum is obtained from clay. And again, if we describe the process very simply, we take clay, dissolve it in a special composition in a certain way, and then pass an electric current through this clay. As a result, one substance is released at one electrode, while another substance is released at the other electrode. The next method breaks material to atoms. This is mass spectrometry, is that the material needs to be literally broken down to its atoms. And mass spectrometry relies on this method. There are also simpler methods, but they don't always work. For example, there's this thing called density separation. And you might think that if you take an alloy made up of different metals with different initial densities, then after we melt it to a certain temperature, the metal will separate by densities. And you'll end up with a tower like this. Remember that childhood physics experiment where substances separate by densities in a certain order. But it can only be applied in certain cases. It can only be applied if we have highly heterogeneous components. For example, iron and some non-metal. And again, a simple example. You may have melted metals before, and you've noticed that slag appears on the surface of the metal. What is this slag made of? What is this? Does it float up? Are those the elements that have a higher density like? You can write in the comments, low density metals float, high density metals sink, removed. Because the higher the density, the heavier the metal is, and the lower it will be in that overall bath. And this floating gunk is usually removed by a special system, resulting in a clean mirror of the metal. And this slag that has risen to the surface is made up of impurities. We should remember one more interesting method. There is something called diffusion mechanisms. Diffusion mechanisms sooner or later try to equalize the structure. Diffusion mechanisms try to lead us to the point where we end up with basically two initial elements. In general, it's not entirely correct to say that, but there are known cases in science where we took an iron sample, and this iron sample, one end ended up being made of one metal, while the other end was made of another metal. And this happened only thanks to diffusion processes. The thing is, the time required for such separation was measurable. Probably not the lifespan of the universe, but decent time intervals. Well, it's time to wrap things up. So, answering a simple but interesting and short question, can you separate an alloy into its original components, or is it physically impossible? We should answer very simply. Physically, it's possible to do that. The thing is, economically, it's completely impractical.